Hello, welcome to another module in this massive open online course. So, let us today, we are talking about the inner product, right, and the correlation between two signals. So, let us look at another interesting example of this inner product, that is with respect to the beam forming, that is forming a narrow beam in a wireless communication system with multiple antennas. So, another interesting example of, and another very important, I would say, this is essentially beam forming So, what is beam forming? Beam forming is essentially, what we mean by this is when you have the receiver in a communication system, right, and we have multiple antennas at the receiver, and we have a user, right, who has, let us say, a cell phone, okay, and then what can, so these are the antennas. So, each of these is an antenna. You have several antennas, that is, you have these multiple antennas. So, beam forming is only possible when you have these multiple antennas, and what you can see is that you can form a narrow beam towards a particular user, that is, form a narrow beam what we term as a beam, and this enhances the signal to noise power ratio, enhances the signal quality. And this is a very important thing, significantly enhances the signal quality, in fact I would say significant. So much so that if you have essentially L antennas, you can show that the signal to noise power ratio, that is the signal quality, can increase by a factor of L, which means your signal reception is going to be much better when you have multiple antennas, and you can do the optimal signal processing or the optimal beam forming with these multiple antennas. So, theoretically the signal quality or signal to noise power ratio, so with L antennas, signal quality increases by a factor of L. This is a very important result, and all this is because of this essentially what we call as, and this process is essentially what we are terming as beam forming, that is forming this narrow beam towards a particular. So, the narrower the beam, better the signal quality, and this process of forming this narrow beam, this is essentially what we are terming as beam forming, and which is a very, very important aspect in modern wireless communications, especially if you look at 4G, 3G, 4G, 5, in fact in 5G it becomes all the more important, because in 5G you have a very large number of antennas, massive MIMO systems or millimeter wave. So, we will talk about some of these things. So, the larger antennas, which are basically hundreds of antennas, so naturally beam forming becomes very, very important, right, especially as the number of antennas becomes large. So, this is a technology. So, this beam forming is a technology that is actively used in, I would say, 4G and also 5G, and also we can also say to some extent Wi-Fi. So, very, very something that is very, very important. Okay, excellent. So, how do we model this beamforming system? Let us look at a system, as I said, with L receive antennas. So, you have the L receive antennas and you have the mobile of the user with a single antenna. So, this is your mobile, let us say this is your base station, which we also call as the BS, and then what happens is you have the channels between the mobile and the base station. These are denoted by this channel coefficients H1, H2, HL. So, these are basically what we are calling as the channel coefficients. These are essentially what we are calling as the channel coefficients. Now, what is going to happen with these channel coefficients is now we are going to have, so with these channel coefficients, so these are, so HI, so these are L antennas. So, this is antenna 1, antenna 2, so on, antenna L. So, you have the L antennas and HI is the channel coefficient. In fact, one can also call this as the feeding channel coefficient, and the output symbols on this L antenna, we denote them by Y1, Y2, YL, and the transmit symbol is X. So, Y1 or YI equals received symbol. You can say this is the received symbol, or you can say output symbol. Antenna I, HI is the feeding channel coefficient, X is the transmitted symbol, correct. So, X is so yi is related to X as essentially yi equals, we say, channel coefficient HI times the transmitter symbol X plus the noise. So, obviously, you are always going to have the noise. So, the noise, that is essentially the noise. So, this is your noise power. So, this is the noise on antenna I. So, essentially what you have is you have the model for antenna I. Okay. So, you have the, this is also called the system model, or you call the input output, or you can call it the I/O model for I/O model for antenna I. So, essentially you will have a system that is essentially, basically, if you look at this, you will have Y1 equals H1x plus N1, Y2 equals H2x plus N2, so on. So, you can have Yn equals, I am sorry, YL equals HLX plus NL. These are the models for the L antennas. So, this is basically, these are the models for L. These are the models for L antennas, right. So, you have yi equals hi times x plus L. You write them for each of these individual antennas. So, you have y1 equals h1x plus n1 and so on, and now we stack these as a vector. all right. So, now interestingly you can put these things as a vector. So, this becomes your y1 y2 yl vector, h1 h2 hl, that is your channel vector, and n1 n2 ll, that is your noise vector. So, essentially you can write this as the vector model will be y1 y2 yl, this is equal to h1 h2 hl, right. So, times x plus n1 n2, and also you have y bar, you have h bar, you have n bar. So, essentially you can write this as y bar equals h bar x plus n bar. So, this is your output vector, this is your channel vector, this is your noise vector. Now, to perform beamforming, right, we want to perform, the idea is, remember we started with this idea that you can form a narrow beam and maximize the signal quality or the signal to noise power ratio. So, to perform beamforming, for beamforming what we do is essentially we perform what we term as a weighted linear combination. That is essentially what we write is we have W1 conjugate y1 plus W2 conjugate y2 plus so on WL conjugate YL. So, this is your essentially your weighted linear combination, right. So, this is your weighted linear combination of the outputs, which you can write as the row vector, that is your W1 conjugate, W2 conjugate, WL conjugate times y1. So, this is essentially what you call as write as W bar Hermitian. This is of course your output vector, a signal vector y bar, and this W bar Hermitian. So, what is W bar Hermitian? You have this vector W bar of the weights, right. So, you have the W1, W2, WL of the weights, you take the transpose and the conjugate of each element, that is column vector becomes a row vector, and then it becomes each element we take the conjugate of each element, alright. So, this W bar, this is called as the beamformer or the beamforming vector, alright. So, this W bar, this is formed as the W bar is called as the beamformer or the beamforming vector, and this can be chosen to maximize the signal quality. And what you can see over here, it is very easy to see, is that this is of course your W bar Hermitian y bar. So, you are forming the inner product of the beamformer and output vector. So, this is essentially inner product of beamformer So, this is essentially the inner product of the beamformer and the output vector, right. So, you can clearly see the inner product, right, or the correlation, right, has a very important role to play in beamforming. So, you have the beamform vector, the beamformer W bar, and you are forming its inner product with the output vector. Now, how to choose this beamformer? W bar is termed as the beamformer. Now, choose the beamformer. How to choose W bar? How to choose W bar? Well, the optimal W bar, what do you mean by optimal? Which means the beamformer that maximize optimal W bar that maximizes the SNR or signal to noise power ratio is W bar equals H bar divided by norm of H bar. You see, this has a very interesting property. This is basically similar to the channel vector, but normalized, that is unit norm. Remember, H bar divided by norm H bar. This is a unit norm vector, right, and this is similar to the channel in the sense that it is matched to the actual channel vector, that is H bar, right. So, this is also is known as a matched filter, right. So, essentially what you will see is, first of all, this is a unit norm vector, and this is matched to the channel. So, this is also a matched filter, and the other thing, interesting aspect is this maximizes the signal to noise power ratio, correct. Hence, this is termed as, it's in more popularly it is known in wireless communication technology as the maximal ratio combiner, MRC. So, this is simply known as the maximal ratio combiner. Maximal ratio combiner, that is the optimal beamformer that maximizes the signal to noise power ratio at the output of a multiple antenna wireless communication system. We also call that as a CMO, that is a single input multiple output, because we have multiple antennas at the receiver or multiple outputs at the receiver and only a single input, right. Of course, we are later going to see MIMO, multiple input multiple output, but here the context of this beamforming, you can easily understand it from the CMO system, single input multiple output. Let me also just mention that, because you might find that useful. So, you go all the way back over here, this is what is called as a CMO. That is single input CMO system, or a single input multiple output system, a very important class of wireless communication systems, right. So, you have multiple antennas at the receiver, and in that what we have shown is that the optimal beamformer, right, optimal, which maximizes the signal to noise power ratio, is given by the maximal ratio combiner. So, this is a very important result, a very interesting result, and this has interesting applications in modern wireless communications, especially I told you 3G, 4G, 5G, wherever you have multiple antennas at the base station, multiple antennas at the handset. This is, I mean, multiple antennas at the base station here, what we are considering, but you can also extend it to a scenario where you have multiple antennas at both sides. Alright, so these are the interesting applications, and there are a lot more interesting applications of linear algebra, and in particular this particular concept, that is the inner product or the correlation between these two signals, right. Alright, so let us conclude this module here and let us continue in the next module. Thank you very much.